Okay, we're back on gas laws 2 here. A moment ago we talked about Boyle's law, and we talked about the relationship of as the pressure went up, or as the volume went up, the pressure would go down, or as the volume went down, the pressure would go up. Well, in Charles' law, we're actually looking at volume related to temperature. So if we have a flexible container and we want to keep the pressure constant, and so we don't want the pressure as we heat this thing up, we don't want the pressure increasing. So what we have to do is we have to, as the temperature starts to rise, we also have to increase the volume of the container. So in this particular case, you'll notice the graphics at the right here. As we start to warm this up to keep the pressure constant, the volume of the container is also going to have to get bigger. And so the way that this set up, notice here it says V1 over T1 is equal to V2 over T2. Well, a moment ago we said, really what this is that volume 1 is equal to a constant times the temperature, or we should say V is equal to a constant times the temperature. And again, as we look at this equation, this would be, we want to get this K by itself, and so what we get is V over T is equal to K. And again, we have two situations, and if those factors of pressure stay the same and the atoms stay the same, then we can start out and say V1 over T1 is equal to K, and that V2 over T2 equals K. And again, we end up with this equation over here on the left that says V1 over T1 is equal to V2 over T2. Now, again, we can use, all we have to do now is find out if we have V1 over T1 and V2 over T2, and we start to calculate what one of those variables is going to be missing. So as we move on, we slide to the next screen. Here's a situation for us, and if we look at it, it gives us our volume. So we got a volume of 45 liters, and we'll put down 1 for that because we'll find out what that is. We have 250 degrees Celsius, so T1 is 250 degrees Celsius. And we're going to increase the temperature, so we got a T2 of 550 degrees Celsius. Now, in this particular case, what we have to do when we're dealing with temperatures in gas laws is we have to consider the absolute scale. We can't work in Celsius. So what we have to do is we have to convert everything into Kelvin. And as we do that, if we start out with 0 degrees Celsius, well, that's equal to 273 Kelvin. So what we need to do is with the 250, we need to add the 273. So as I add 273, we can get this into the Kelvin scale, which is 523 Kelvin. We need to do the same thing for the temperature in the temperature 2, which gives us 823. And so we have our two new temperatures. We set it up just like we did earlier, where I have 45 liters over the initial temperature, 523 Kelvin, is equal to, we don't know the new volume, so we do volume 2 times 823 Kelvin. Now, the math for this, if we do the algebra for this, what we're going to do to both sides is we'll multiply by 823 Kelvin on both sides, and the 823 Kelvin on this side divides out. And what we need to do is take 823 times 45 divided by 523, and that will give us our new volume. Okay, so that was Charles' law. That's volume 1 over temperature 1 equals volume 2 over temperature 2. Gay-Lussac is the same, is dealing now with pressure and temperature. So what we're going to keep constant in this particular case is the volume. And many of you guys have experienced this one, where if you start to heat up a container, what happens is the pressure starts to build inside that container. I always think the classic example that I remember as a kid is somebody walks by a bonfire and drops in a soda can. If the soda can is sealed, it doesn't want to change in volume. And what occurs is that we start getting a buildup of pressure because of the temperature increase, and eventually the can bursts because the volume won't change. And so the same type of problems as we did earlier with Boyle's law and Charles' law. Now, the nice thing is these three laws all deal with pressure, temperature, volume. Each of them only dealing with two at a time. So what we're going to do is we're going to compare these and come up with a law that might cover all of them. So we know that P1V1 is equal to P2V2. We also know that V1 over T1 is equal to V2 over T2. And we know that P1 over T1 is equal to P2 over T2. So if we looked at all three of these equations, you'll notice that pressure and volume are together. And so if we put pressure and volume together, they are also both over temperature. And so if we put them completely together, what we'd get is we'd get this P1V1 over T1, which would equal P2V2 over T2. And this is actually called the combined gas law. And the combined gas law, I better rewrite it for you here, P1 over V1 over T1 equals P2 V2 over T2. Now, what you can do is, currently you have four gas laws. You have Boyle's law, Charles' law, Gay-Lussac's law, and now you have this combined gas law. With the combined gas law, though, you really only need to memorize the combined gas law because the other three are contained within it. If the volume stays constant, you can ignore it. If the temperature stays constant, you can ignore it. And so if you'll notice, this one gas law covers all of those things. Now, so again, it's putting in the values and solving for one of these variables. So we're dealing with an algebra problem for this particular situation. Again, thinking about temperature always having to be in Kelvin. Pressure can be in any of the three units. Volume could be in milliliters, liters, kiloliters. It could be in different volumes, and that would be fine, as long as both sides are in the same. So if one side's in liters, the other side also has to be in liters. Now, we've dealt with temperature, pressure, volume, and if you remember a moment ago at the beginning of this thing, we talked about the number of molecules also. You know, how much stuff is actually in there. And what we do with how much stuff is in there is actually called the ideal gas law, and I'll try to do one more video containing the ideal gas law in just a moment.